Good, live stream should be running. There we go. Hello everyone, welcome back. Hope you're all good. You can vote on the new slider question while you're settling down. As you may guess, we're talking about compression now, as I already announced last week. One other announcement. I mean, you keep going on the Bamboo assignment. I see there's much more things coming up in the scoreboard now. The other thing, please have a look at CampusWire at the questions. Even if you don't have a question yourself, check if you can answer some of the questions that are posed there. It's quite helpful for some of you to answer those for yourself and for the others people's sake. Apart from the bonus points on the class test mark that you may remember. The questions I saw on CampusWire are not really urgent, so I'll give you a few days, and then I can say something about it. But it's really more effective for everyone if you keep answering questions and posing. I'm not even sure I know what Huffman cider is. I hope that's not apple cider. I'll look it up. I think emoji are a good way of compression too, right? In one character symbol, you can express an entire feeling. Pretty effective. What does this mean in numbers that a few people have seen Huffman? There's 4 votes. I think the animation makes it look like there's half of the people voting for Huffman, but this is not quite true. I love the right-click zip one. We'll talk about zip, actually. I mean, what's behind it, in case that helps you. All right. What's the default method you would use if you compress files and send them to someone by email or something? Would you use zip? Would you use something else? Yeah, RAR's still around. I think it's still proprietary, right? But it's often better than zip for mysterious reasons. I think the new kid on the block, and new in quotes, is 7-zip, if you've seen that. As maybe the continuation of RAR. It's a little freer. It's kind of free to use, but it's also part of it is proprietary. It often has the best compression ratio, is much slower than the others, but it's often a bit better. Has anyone heard of bzip2? Well, in a week's time, you will know more about it than you may have ever wanted. It's not as well known, but deserves to be more known. All right, thanks a lot. We'll briefly come back to that in a second. So again, the usual pattern. There's quite a few people who have seen Huffman, which will be one of the chapters. But then if you look at the fraction of people, it's maybe a third. So, or maybe a quarter, which would match the advanced computer science students by numbers. So I'll try to cover this pretending that you haven't seen much of it, because that's true for most. Okay, welcome back to COMP526. This will be the second big unit where we talk about text after the long unit on text indexing last time. This time we'll talk about compressing text. And this will also keep us busy for a while. Then if you're afraid that we'll keep going like this, the remaining units are much smaller. 6 and 7 are definitely more than a week's material, and 8 will be quite quick, and 9 will be quite quick and not part of the exam. So the bulk of the material is done after this one. But not so fast. We have one really exciting unit to go. again, I love this unit. There's quite a few really cool concepts in there. Again, if you stitch them together, they appear to achieve quite remarkable things. But each individual one is doable with sitting down, a bit of caffeine, and some patience maybe. So let's dive into this. What I want you to take from it are a few things. I want to talk about the basics. I want you to take that from this unit, that you know what's behind ASCII and UTF-8 and Unicode and more generally. I want you to not only be able to right-click and say zip, I want you to understand what are the limits of what can compression do, at least lossless compression. And we'll look at a collection of methods that people have invented to compress. Some of them just real quick. But I think it's useful to survey those a bit so that you know what is available, how they belong together, and what their properties are. And then a last one on the application side of things, so the higher level of the Bloom's taxonomy, if you want. I want you to, if you have some specific scenario, I want you to be able to figure out what could be an effective way to compress this specific data that you're dealing with, because that's most likely to be the scenario where you would craft a new way of compression. Many of these techniques we'll talk about are good general purpose compressors, but if you know more about the data you're dealing with, sometimes you can outperform them. Okay. I divided this up into a lot of subsections, so each of them shouldn't be too long. And you see in many cases, this is really one subsection that should be one by topic, but I split it in two to have bite-sized chunks videos, or well, big bites sometimes, 20 minutes each, roughly. Let's first talk a bit about why we use compression, what we use it for, and a bit like in the string chapter in Unit 4, a bit about the notation that we'll use so that we're all on the same page for this. We've been talking about strings for a while now. We've been talking about finding patterns in a long text. That was units 4 to 6, especially units 4 to 5. We were given the text, the pattern, and then we tried to find something. Unit 6, we will try to build some data structure out of the text so that the pattern searches afterwards become faster. And now we'll shift the focus a little bit from working on the text to storing and transmitting the text. So we try to be more frugal on space. That's what compression, after all, is about. But it's not only that. It also means often if you compress the data, it also becomes faster to work with it. And that often has to do with the fact that on modern machines, accessing memory, or if it's over network, even more so, the bottleneck is getting the data to you, not so much working on it in many cases. Okay, the way we store and transmit strings is about computers. We won't talk about analog measures or analog ways of transmitting data here. So everything has to be binary at the end of the day. We want zeros and ones because that's what our computers can work with. For the transmission side, there's an orthogonal axis. If you think about, well, Wi-Fi communication or the cellular network, there's interferences, and you would like to transmit even if the channel, the medium you're communicating over is kind of noisy, lossy, and is not perfect. We'll briefly look at Unit 8 at a simple way to do that. That's kind of complementary to compression. You first want to compress the data so that you minimize the amount of data you have to send. But then you probably also want to build some redundancy in again for the transmission itself. But this depends on the medium. If you communicate over a very reliable network, you might not need this, or you might only need a very little bit of redundancy. So for this unit, we'll only focus on the part compress the data we have as much as possible and assume the storage medium or transmission medium is perfect. So much for the context where this fits in. I want to briefly show this for the video again. So I asked you what types of compression algorithms you already know. And a few people knew Huffman Codes, many other interesting variants, and a few that I don't know. There's a few terms also, lossy versus lossless, that we'll pick up. Okay, before we keep talking about this, let's fix the terminology so that it's clear what the vocabulary means that we're using. In compression, there's always a source text that we start with. And then we compress this to a coded text. And that's the compression direction. Which we call encoding. And of course, compression algorithms are only useful if you can also invert that process, if you can get back from the coded to the source. And that's then the decoding step. So source text and coded text is data, and encoding and decoding are two algorithms. Okay. What's to be stressed about the source text? It can come over any alphabet. Whatever the user or the application dictates is useful. We'll often assume that this is ASCII or the Unicode alphabet, but it could be different. Could be RNA sequences, DNA sequences, so that's a smaller alphabet. The thing is, we don't have really control over the source alphabet. For the coded strings, we determine what we want to use, but almost always we'll use binary because we want a binary representation. But we'll sometimes deviate from that because good compression algorithms often are a chain of different things. So you first apply some algorithm that spits out some intermediate representation, which is fed into another algorithm. And so for this first step, it might make sense to not immediately go to binary, but to go to something else. That's why we keep it general in here. Okay, so these are just these two alphabets. Any questions so far? Compression can be lossy or lossless, and it depends on the application what makes sense. In lossy compression, this arrow back, going back to the source text, means only in an approximate sense. So you can get something that's close to the source text back, but not exactly the same. So the prime example is all sorts of multimedia that you know, and I don't have to explain much, right? If you take a picture with your phone, it's immediately compressed to JPEG. If you have a fancy phone, it might also store this raw data format, or if you have a proper camera. And that stores exactly what the sensors in the camera give back without compressing it. And there's more color depth and more information in there. Whereas the JPEG loses some of that information, but the file size is more reasonable then. So that's often what you do for multimedia, and we will not look at this here. That leads us too far, and in particular, to do this, you kind of need a way to tell when are two pieces of data similar enough for you to accept it. And that's highly dependent on the data. If you look at pictures, then it's not even clear if you can formally define this, but if you show it to two humans and they say, yeah, this looks the same to me, that could be a measure. It's not so easy to automate this. So in a way, we'll avoid this by only looking at lossless compression here. So we want to get back the source text bit by bit or character by character as it was. No deviations allowed. And of course, the benefit is that you can use this wherever you want to deal with data. There's no implication of using the compression in between. Is transparent to the application. The downside, of course, is, as you may know, from FLAC audio versus MP3 or something like this, lossless compression has higher compression ratio just because it can throw away information. There's limits to what lossless compression can achieve by contrast, and we'll talk about those limits. There's many ways how you can determine for the different compression methods that we'll talk about which one is better than another one. I just want to list different ways to look at this here. We will mostly focus on the size. So we want to get a coded text that's as short as possible. But there are other dimensions in applications that might be even more important depending on what you need. It could be more important that things are fast. That's, say, you build a little hardware router that has to forward gigabit Ethernet traffic. You can't spend a ton of time compressing each packet. You probably just want to forward it as quickly as possible. But if you can build something that works fast enough and compresses a bit, that might be good. We'll talk about this in Unit 8. Some compression is slightly more suitable if there are errors in the transmission. But again, the proper way is rather to first compress and then apply other techniques. Completely opposite topic, something close to compression is encryption from cryptography. There, the goal is not to make the coded text smaller, but to make it jumbled and hard to read for someone that it is not intended for. There's many similarities between compression and encryption, but the key difference is the size is not the big concern for encryption, but rather it has to be hard to invert without the key. Integrity goes a bit hand in hand with that. We'll not really look at that today. So we'll focus on the size, and we'll measure the compression quality in terms of the compression ratio. You probably have an intuition what the compression ratio is. It's the length of, so this is the length of the coded text. I should say a size, not length. So it's essentially dividing the size of what comes out, dividing by the original size. But we have to be careful how we measure size, because we have strings over different alphabets. So if I'm encoding something in binary, I need more bits, I need more characters than when I'm encoding something with a huge alphabet where each character has many different possibilities. And the proper way to include this is to take the log of the size of the alphabet, because that's the number of bits you need to specify any single character if you don't do anything more complicated. So we'll just define the compression ratio like this. The length, the number of characters in the coded text times the log of the size of the alphabet. And for the source text, we divide by the number of characters in the source text times the log of the alphabet size again. And of course, in the typical scenario where we encode to binary, this is just 1. So the compression ratio should really be below 1. That means we have achieved something. We made the thing smaller than it was before. If we keep it at 1, we haven't really gained much, but at least we haven't lost anything. If it's bigger than 1, we lost something. Then we made the text bigger. That sounds not like compression, but we'll see that this is effectively inevitable. Now that we have a way to say what we would like to achieve, we want to minimize the compression ratio. We might want to think about how good that possibly can be. One thing that's like in previous previous units, we'll have to think about whether we're talking about the worst case or average case or best case. For compression ratio, we usually talk about the given case. So we have a specific text and we look at that one. But for an entire compression algorithm, we would ideally like to have a statement that is always as good at this. And we'll see how far we can get towards that. There is another take on this, which comes from a completely different idea. And so you might recognize this picture as something you may have seen. Does anyone know what it is?
The fraction is going to infinite.
Yeah, it's a fractal. I think is the Mandelbrot set. So it's well, it's related to a specific equation, and you can give it nice colors by the number of iterations you need to reach it. It's an innocent question. Here's a picture. Can you compress this losslessly? And suppose I'm fixing the resolution to a certain number of pixels. So it's quite well defined. But can you compress it or not? If you look at the picture as it is and use PNG is an image format that does compression, but lossless compression by default. If you feed this image into PNG, it won't compress much. A little bit, because PNG will pick up that there's areas here where the picture is almost just one color over a large range. But there seems to be these highly complicated regions that are, for PNG, not really compressible. But the amazing thing, because we know where it comes from, is you can compress it very much to a really tiny program, because this picture, after all, was generated by a computer program. So wouldn't the ultimate compression be just that program? So you give me a program that produces the data. That's the ultimate compression, because it's the best you can possibly achieve in a decompression step. Decompression has to take from a certain input, and here the input is the program itself. The decoder has to somehow take the coded text and produce the original source. Now, an absurd limit of that is I don't code anything at all. The coded text is the program itself, and you just run that to produce the source again. That is an option, and people have studied this. It's known as Kolmogorov complexity. So the size of the smallest program that outputs a given source text, that's its Kolmogorov complexity. You'll have to be a bit careful what types of programs you allow, but suppose you fix our good old RAM model or a Turing machine. There's ways to make this very formal, and then you can study it. But there's a big caveat with this. And now for this one, it depends on your background. If that statement makes a lot of sense to you, it turns out finding the shortest program is a really hard problem. It's not just slow to compute it, it's utterly impossible. It's an uncomputable problem. So you may have heard of the halting problem. The question, here's a program and an input. Does this program terminate on this input? And Alan Turing famously showed that this is impossible to do. It's not just that it takes a long time or so. It's with the computers that we envisage, it's completely impossible to do it. And the same is true for finding the Kolmogorov complexity of a given input in general, at least. So we have this wonderful notion of ultimate compressibility, which is also utterly useless because you can't even evaluate it. You can't even, here's a given piece of data, tell me how complex it is. It's impossible to answer this question with a computer, at least in the general case. There's no program that always works. So in a way, the whole rest of this unit, if you want, is trying to work around this. Try to get, on the one side, statements. You can't possibly compress data like this more than that, at least under some assumptions. And on the other side, complement that with concrete compression algorithms that work reasonably well for many types of data, and you can show that they achieve certain guarantees. Okay, this is all without making this concrete. I think it's not so useful. You can try to work on both sides, try to show that you can't compress more than that and give algorithms that compress to a certain degree. But we'll have to live with a certain impossibility here. We won't ultimately solve this. There's always the possibility that you can come up with a slightly smarter compression algorithm that just approaches the problem differently. Okay, so it seems pretty tough if from looking at data, even as a human, it's hard to figure out if it's compressible or not. Maybe we have to be a little less ambitious. And instead of trying to capture ultimate compressibility, we'll look at certain features that definitely mean that data is compressible in some way. And we'll focus on two types of redundancies in the source text that make the source text compressible. One is that if I called this here uneven character frequencies, because I didn't want to throw around terms that we haven't introduced yet. The idea is, suppose you have English text. There's just many more vowels, and E is much more common than what's the least common in well, X, Q. Q is probably not too common. X, not too common. What I'm getting at is some characters occur much more often than others. And at the moment, or the trivial encodings that computers use, and we'll touch on that, they don't make any use of that. And the second way things can be redundant is if there's repeating parts. That's maybe more intuitive, the second part. If there's the same text appearing twice, then there should be a way to just store it once and refer to it back. That's the core idea in the second part, but making this automatic so that it always works is a little tricky. Also, I want to point out, if you take your worst case classes out and you ask, if I have some compression algorithm, what's the worst case compression ratio of all source texts of a certain length, say? You will be very disappointed, because that is always worse than 1. It's, in a sense, with lossless algorithms, it's impossible to always compress. And this is a very simple very simple proof that you'll do in the tutorials. After you've seen it, you will say, yeah, of course not. But it's kind of insightful to do it. So I'll refer you to the tutorials for that. But if this sounds like surprising that zip doesn't always work, in a sense, wait for the tutorials. And a fun experiment that you can do in preparation for that: what happens if you zip a file and then zip the zip file again? Has anyone ever done that? Yeah? Yeah. So if you zip it again, it doesn't get any smaller. And if you pay close attention to the exact byte count, I think it actually gets bigger. Ever so slightly. Like, it's not very noticeable. But if you keep doing it, first of all, it doesn't improve. And second, it actually gets slightly bigger. And that's ultimately because of this. There's just no way that if zip didn't pick up the redundancies in the first round, it won't pick them up later. And there's files that are just incompressible. All right. I should say, for each compression algorithm, there are files that are incompressible. It's not that there's one hardest file that is incompressible by any algorithm. That's a different statement, and that would come down to Kolmogorov complexity of that string, which we know is very hard to get at. But for every compression algorithm, you can find an input where it utterly fails. But this might be a different input for different algorithms. Okay. With that said, let's have a look at the first part, where we look at character frequencies. Before we start with something more fancy, let's look at the simple ways how we represent strings in a computer in the first place. And this is all about computers work with binary, but we like our alphabets with Latin letters or whatever other scripts. And so we need some way of going from these alphabets to a binary representation in the computer. And so what we need is an encoding function, which assigns to each letter of our source alphabet, say the English alphabet, some representation in binary. Now, we can't just use one bit. It will be a string of bits. We often have many more characters in our alphabets. In particular, if this is binary, that's kind of always true. One piece of terminology will call the binary string that encodes a single character the code word of that character. And what we'll first look at is a fixed length code, where every character gets the same number of bits assigned, a code word of the same length for every character. And then we'll generalize this to cases where this is no longer the case. And here's probably the simplest, most well-known fixed length code. That's the ASCII character set, character encoding. And it's just given here on the slide. So here's a binary pattern. And then behind the pattern is what letter it represents. The sensible letters start around here. So this is a space, right? That's why you can't see it. And then there's some punctuation marks, the digits, uppercase and lowercase letters. That's pretty much it. If you try to represent some other European languages or non-Western languages, you're pretty much out of luck. There's 2 columns of these weird control sequences. That comes from the fact that ASCII was invented when people had needle printers, and you used this. These are told to used to tell the printer where to move the printing head and things like that. So many of them don't make a ton of sense anymore. But we still use carriage return for starting the next line. A new line is there somewhere too. Well, can't find it. This is line feed. Well, you will know text files on Unix, Windows, and Mac are encoded differently in that the line ending, the new line character, is a different one in each case. That's using some of those. Apart from these weird control characters, it's pretty much a mapping from the English characters to a bit pattern. Each character is mapped to 7-bit, so you can represent 128 different things. What's good about these, they're very simple. And so encoding and decoding is almost instant. You can do this very close to the hardware, so it takes literally just one processor cycle. In terms of compression, this doesn't really compress much. It doesn't compress at all. If you have a text that consists of just all A's, it would need the same space as some complicated Shakespeare play, whatever. It's also not really flexible. If you notice you need other characters, you're out of luck. And so you have to invent a bigger alphabet and find a new encoding. And this has plagued much of the computing industry in, I guess, the 70s, 80s, before people started with Unicode. If we don't want to upfront fix the code length, we can do something else, and that also is not a new idea. We can assign code words of different lengths to the characters if we're a little careful. And here's a very old variable length code. That's the Morse alphabet. Or, as I learned, there's different ones, but this is the international Morse code. which has just the Latin letters and digits. And so I guess you know this. You can use this to send letters over like a wire or just by making sounds. And then the dot is a short node, and then the dash is a long one. And so one way to say if you want to encode, then you want to use this table on the left, where you find the next character that you want to encode, and you produce that sequence of tones. If you receive something, at least in your head, you probably want to do rather what this tree says, what this tree shows. You start in the root, and then you either hear a long sound or a short sound, and that makes you go into a different branch. And then there's the characters. If you end up at a certain point, then the characters tell you what letter that corresponds to. Okay? It's quite typical that we have two representations of a character code, where one is convenient for encoding and the other is convenient for decoding. And so if you were to implement a compression method, you often represent the code in different ways in encoding and decoding. A cute little side remark, and to wake you up as well. What's the coded alphabet size in the Morse code? So this is testing the terminology and a nitpick of Morse code. We had an amazing 41 votes for the first question. So pay close attention to which alphabet the question asks for. Okay, we're getting close to the number of people from before. Okay, let me show you what you've voted, and it's a few more down there. So this is a big peak for 36, and some votes for pretty much anything. So if you read the question carefully, it's about the coded text. So we're not asking about how many characters can you represent, not A to C plus the 10 digits. But why is the correct answer 3 and not 2? Because we have dot and dash. That sounds like 2. The thing in Morse, it is a little cheating. There's a third character, which is pause, end of a character. If people use Morse codes, they leave a little silent period between the characters so that you know when one character is over. And if you look at this decoding tree, you see immediately that you need this. Suppose I hear one short sound. How do I know whether I should continue from here down when I hear the next thing, or whether I should stop and say, oh, that was an E? There's no way for me to tell unless the other person gives me the pause to signal that this is the end of the character. So Morse code really uses 3 characters, the 2 shown here and a break, end of character. Okay? And yeah, you need this if you have a tree like this. That's another thing we'll come back to. There's one more variable length code that I bet you all know, and I bet most of you don't realize it's variable length. But if you thought about it for a minute, you notice it has to be. And that's UTF-8, or UTF-16 is similar. That's the standard way to code text files these days, since at least 20 years, I guess. It took a while on the web to convince everyone, but It's a way to represent text files that can contain any Unicode character. And remember, there's some 150,000 of them, although most of them are not used very often. And so UTF-8 is designed around the idea that most of the time people use just the ASCII characters with a few extra characters from the full alphabet, like all your emoji. They're all just one code point in the Unicode alphabet. But if you send text, maybe the fraction of emoji is rising, but you still, by and large, on the text have more of the traditional characters. At least that's the assumption UTF-8 is built on. Okay, it can represent any Unicode character, and there's more than 100 or more than 256. So the UTF-8, 8 stands for 8-bit. It hopes to represent most characters with just 8-bit. But that would mean you can only represent 256 different ones. Doesn't work for all of Unicode, so it has to do something different. And what it does is it uses between 1 and 4 bytes for one character. The ASCII characters are encoded in 1 byte, and there's a leading 0. Remember, ASCII is 7-bit, add a 0 in front, that makes 8-bit. So that's fine for representing all those with just a single byte. If you need any of the non-ASCII characters, then things are slightly more complicated. And in a sense, there's different regimes. There's the Unicode alphabet is broken up in different ranges, and depending on where it is. So this is the Unicode character in hexadecimal. If it's ASCII, then it fits below this. So 7 and F, that's 7 ones written in hexadecimal. If you're above that, but below the next more 4 more bits, then you get represented with 2 bytes, and the X's are replaced by the actual code point, and so on. So it's, I know it's a bit tedious to read. And you see that there's a special way to signal how many bytes each character will take. So if you read Unicode, the next byte, if it starts with a 0, you know it's just a single byte character, an ASCII one. If it starts with 2 ones and then a 0, you know it's 2 bytes that are coming. And you have to puzzle out the X's to get the character. And each byte that is not the first one is starting with 1, 0. And here you have 3 or 4 ones to signal that there's more bytes coming. Why do you think do we need this 1, 0 here to signal that this is, why do we do this in the next bytes? We could have just left it out, because this already tells you how many bytes are following. Any guesses? So people do this for convenience. If you jump into a Unicode text at a specific byte index, and you see that the byte starts with 1, 0, you know you're not actually looking at the beginning of a character, but you're somewhere in the middle of the previous character. So you know not to start to decode from there, and instead you skip over all the bytes that start with 1, 0. It's just a way to trade space for convenience. You could have done a fewer bits if you were just after compression. But since this is also used as a way to represent strings in memory and compute over them, it turns out it's more convenient to spend a few bits here to make access more efficient. All right, so UTF-8 combines the space efficiency of ASCII for the characters where you just need this English language letters. But you have a way to represent any other characters when they occur, just using a little more space than for those. So that's one example of a variable length code that you've probably been using all the time without maybe thinking about it too much. The flexibility does come at a price. If you use a code that has variable length code words, you can get into trouble. And I want to illustrate the trouble on an example. Suppose you have this, this code. So that assigns to the 4 letters in our alphabet some code word. Now I can use this to encode a string like banana into this binary representation. And you see the B corresponds to 110, so I write 110, then comes an A, single 0, and so on and so forth. Okay? I hope the encoding step is clear. You just concatenate all the code words for the characters. Now, if we try to decode this bit pattern, there's another way to read it. We can say this could be BA, but then SS instead of na. Because 100 is also the code for S and for N and A concatenated. So there's 2 ways to decode. That's not good. So it's an ambiguous code. And of course, if you look at this, you immediately see that if you write an NA, it leads to the same code as a single S. So there's trouble ahead for sure. But if I just showed you this code and asked you, is this code good or not, it might not have been completely obvious that it is flawed. In this example, of course, it's clear, but how can we avoid creating codes that have this ambiguity? We can't tolerate this. It's not a way we can live with. We want to be able to reconstruct the source text exactly. In general, this is relatively hard, but there's a simple sufficient condition. What made this code nasty is that one code word, 10, is a prefix of another code word, 100. So when you decode and you read this 100 pattern, you start reading 1 is not a code word, so I can't stop. 10 is a code word, so I could stop, but I could also continue. And at this point, the decoder doesn't know what to do unless you help him out. If, by contrast, our code has the property that no code word is a prefix of another code word, then the decoder never gets into this problem. It always knows as soon as it has found a code word, it can stop, and it's unique what it decodes to. And so if the code is prefix free, which means no code word is a prefix of another, it is what people call instantaneously decodable. So as soon as you read one code word, you can decode that and go on to the next one. And that also implies that it is uniquely encodable. I just want to point out that there are uniquely decodable codes that are not instantaneous. So you can come up with some complicated code where after 10 characters later, you discover, oh, this is a dead end. I shouldn't have gone this way. But if I take the other way, the other option of parsing this, I would have succeeded. You can build something like that, but it's not really any good. It only makes decoding slow. So we will not look at those. We'll only look at prefix-free codes. But I wanted to point out that uniquely decodable is a weaker assumption than prefix-free. But we'll live with prefix-free. It's good enough, and you'll see in the next section what good enough means. If we have a code that is prefix-free, there's a convenient way to represent it graphically, and that's the code trie. So here's another example of a code, and this one is prefix-free. As you may try to check briefly, no code word is a prefix of another code word. And an easy way to check this is to draw the trie. So you just take the code words and build the trie of this set of strings. Remember, we talked about tries last unit at length. So in the terminology of the last unit, this is the simple trie without any compaction, no suffix trees, right? Nothing fancy. The nodes in the tree just have one child for each possible alphabet character, and you advance with one character on each edge. If you do this for this code, you will see that all the code words lead you to a unique leaf. And that is the signal that the set of strings is prefix-free. And if you remember from the last unit, that was pretty much exactly what we did there as well. We enforced prefix freeness by adding this $sign at the end. And here we say, no, we don't want to add another symbol to our alphabet. We just want to pick carefully a set of strings that already happens to be prefix free. Okay, so the way to check if a code is prefix free is draw the try and check if all the code words are in leaves. And the code try is also a convenient way to decode. Let's do an example. If we want to encode this, this string, then we want to use the table up here, because there we are given by the character what is the code word. So A goes to 0, 1. Then N is 0, 0, 1. And space is 3 zeros, and so on and so forth. Okay, I think that direction is easy enough. The decoding is a little more interesting, so let's do this example at least. We process this text left to right, but we traverse in the try while doing that. So we read the first one, and then the second one, and that brings us to a T. So these two correspond to T. And as soon as I reach the leaf, I know I found the first character. So I cut off these first two, and then start at the root again for the next character. This time I see 1 and then 0 and then 0. So it has to be an O. 1, 0, 0, that's the next cut. And there's the O. One more. We start at the root, 0, 0, 0. So the next is a space. Notice there was never ever any chance for going wrong. There was no choice. There was no ambiguity. I just follow the path. I ended up in a leaf, and then continue at from the root again. Okay? And here are the examples in full detail, just to check. So that's the way we want to think about character codes. I'm only really interested in the prefix-free ones, so it's the same as saying I have a code try of the code words. And that also happens to be convenient for decoding as a data structure to represent the code. Okay, if in general there's the question, how can decoding know what code to use? And that is a real problem if you think about text files and character encodings. You may have seen websites where certain characters just render as some gibberish. And the reason for that usually is that whoever wrote the website was still living in the 90s and used some non-Unicode encoding of the text characters. And your browser, being from 2022, thought everyone has to use Unicode or UTF-8 encoding unless they tell me something different. And so it interprets the file as if it was Unicode, but it actually wasn't. And so some characters look up wrong. It doesn't work. It doesn't break the ASCII characters, but it breaks some others. The reason why this went wrong is someone has to tell the decoder what code was used to encode so that it can apply the right decoding. For ASCII or UTF-8, at least everyone in the world agrees what ASCII is and what UTF-8 is. So it's kind of easy. You just have to tell someone, use UTF-8, and you'll know what's going on. If we use a code like on the previous slide, a custom code like this, I have to tell the decoder what the code was. Otherwise, it wouldn't know what to do. And it turns out this is really a question of the application, whether the code is part of the coded text or not. If the code is fixed and known outside externally, that's what we use for text files and for Morse. If you send your SMS by beeping, then you assume people would recognize that this is 3 short, 3 long, 3 short. Then we don't need to transmit the code. We just assume everyone knows the encoding. If we use what we'll call static coding, where we use the same encoding for the entire text, then we might have to transmit the code because the code is custom for the specific text. But at least it doesn't change while decoding. there's even wilder things that we'll call adaptive coding, where the way you encode the character keeps changing while you're going. In that case, you'll have to somehow tell the decoder how the code changes. And this will often be implicitly in the code. But this is what makes these codes a little more tricky. We'll see example of each of these. So this is just for the distinction of the terminology. Fixed versus static. So fixed coding means everyone in the world knows what that code is. Static means it's the same code for the entire text, but the code still depends on the text. And adaptive is anything else. Okay, sounds like a good time for a break. Hey.
I've been trying to do the programming person. You expected to program, right? That's one of the ways you could solve it, like create a program, try to find.
You can probably solve all of them on a piece of paper as well.
Yeah, that's what Perth is. Right. The way I want to do it is by creating a program.
That's also fine.
Yeah. I'm struggling. I made one initially where it was just like a program and it just chops the tallest thing, and it got the best solution for some. So like the power one is like.
Yeah. It's not a stupid idea to try some greedy algorithm.
Yeah.
It doesn't always do the best.
No, it definitely doesn't. So
yeah.
You can do them without using a program. You just work it out.
Sorry, say it again.
You can do them without using a protein, essentially.
I think so.
Because that power one is huge.
Yeah, okay. So when I say on paper, I don't mean like
Okay.
explore all options. You can work out what the best solution for this one has to be by just thinking over it. And,
Copy and paste.
you know, for this one, it has some structure, as you may have noticed.
Yeah.
And so maybe you can produce an input that's like this one, but smaller, and then solve that first.
Yeah.
That's how you would often solve things on paper, right? You first go to a smaller problem that looks similar, and then work your way up by recognizing the pattern. And the others are a bit more manageable in size, so you can probably figure them out. But for all of them, just going through all possible solutions and finding the best is too slow. Like that's their choices, so that is not the solution. It's kind of boring. Yeah. Also, you don't have to find the best solution, right? It's,
yeah. Well, everyone's already put their things on the leaderboard. I feel like that's what you're gonna get.
Yeah. Well, maybe someone cheated too, right?
Yeah.
You can submit any numbers. I haven't checked that these are realistic yet. All right, guys, everyone recharged, new energy for more compression. I hope you found some time to decompress. Yeah, we can definitely do Huffman Codes. In the next subsection, I want to talk about Huffman Codes, which will be, in a way, the ultimate solution to character encodings. It all starts with the observation that characters come with different frequencies. So here's a list for typical English prose, how often each character occurs. Oh, surprising. Z is less frequent than Q. I mean, this may depend on the text, but if you take a big corpus of text, you will get some frequencies. And you see that they are quite uneven. So it looks like for compression, you definitely want to assign E a short code word and something like these infrequent ones a longer code word. You don't want to go completely crazy about making those 100-bit long or something like this, but you should try to make them longer than the more frequent ones. And if you remember what the Morse code did, it was exactly like that. E was just a single dot, and then other less frequent characters were longer, up to 5, 6 tones. So Huffman coding is all about getting a principled answer to how should you choose the code words. To make this a bit more clear, suppose we have our alphabet. So sigma is the source alphabet, because the coding alphabet will always be binary now for our Huffman codes. And we assume we have some weights. So we know these can be frequencies, but in principle here we just allow any real numbers. So this just tells you how important this character is relative to others. And you want those characters with large weight to have a short code word because they appear more often. Think of the weights as frequencies or probabilities. The goal of Huffman coding is to compute a prefix-free code, so code words for all the characters. In other words, if it's prefix-free, it's a code trie that minimizes now a specific quantity, and that's the coded text length if you weight each character with this weight W. So we're minimizing this quantity. We sum over all the characters. How long is the code for this character times its weight? If you think about a fixed text and you choose W as how often does the character occur in the text, then that's exactly the size of the coded text. Right, so to get this, we want to choose W of C as the number of occurrences of this character in the text. I should say source text, I guess, but you know what I mean. Okay, that's the same as I just wrote down. And in a sense, if we minimize this coded text size, that's clearly the best possible character-wise encoding we can hope for. Because we explicitly say, let's pick the code that minimizes that. So that's the code that gives you the minimal coded text size. That seems like an ambitious goal. And if you think about back to the lesson about Kolmogorov complexity and how these things are all quite tough, maybe this is asking for too much. And then even if we can find such codes, can we find them efficiently? That's even more ambitious. It turns out both things can be done in this case. Because we restricted our attention to character-wise encodings, the world is a bit more manageable. So even a very simple approach that is greedy or myopic suffices. And we'll go through this in a second. So greedy algorithms in general try to do a locally optimal move and then fix that for good and continue from there. And we'll see how Huffman's algorithm for computing the Huffman code is doing exactly that. The greedy step is you find two characters in your alphabet, A and B. So these are just called A and B. These are variable names, right? We find two characters and name them A and B that have the lowest weight among all the characters in our alphabet. That's the greedy step. Now remember, low weight means we want to assign them a long code word. So what we'll do is we will encode them with some prefix yet to be determined and one extra bit that distinguishes A from B. And by doing this, so we set the code word of A as U0, B as U1, but U is not clear yet, so we'll have to figure this out. And the way to do it is that we replace in our alphabet the two characters A and B by an artificial character that consists of both. So I use the same notation for boxes of characters that we've seen for the DC3 algorithm for suffix sorting. This is just my way of saying this is a new symbol and it's supposed to represent A and B, but it's just a name, okay? And important, we assign this new character the weight, which is the sum of the weights of A and B. And then we recurse. So we don't know what U is, this prefix that we'll assign to A and B, but we'll find out recursively because now we have made the alphabet one smaller. We removed two characters and added one new. So if we recurse and find a Huffman code for the remaining alphabet and its weights, this will come back with a code word for this new character AB, and that's our U. That's the shared prefix that we add to them. Okay? If you've seen this before, this might not be the way it was described. There's another way that you'll see in an example in a second that you might recognize. Before we go there, I want to point out that you also know an efficient way to implement this strategy. This step one sounds like you have to, in each iteration, so sigma times in total, you have to find the two minimum weight characters. But if you're smarter than just doing this iteration each time from scratch, you keep the characters in a priority queue. And then this first step is just two delete min calls. So at the same time, you get the two characters with the minimal weight, and you get them out of the data structure. And then you insert a new character with the sum of weights. So that nicely fits the priority queue abstraction as we've learned about in Unit 2. Let's see a small example how this looks like. And it's visualized here by computing this code trie. That's usually the way this is explained. So here's a little source text. It has these 4 characters, and they appear with frequencies 1, 2, 1, 4. So you start with your characters each as a singleton leaf in the yet to be completed code trie. The first step is to find the 2 with smallest weight. So these 2, they have minimal weight in this example. And now Huffman's algorithm says recurse on this and the character EO that you form. And then at some point you will know what is the common prefix of the code words for E and O. Another way to express the same thing is say, we don't know where this is eventually ending up, but as a code trie, there's one node where these 2 are branching off, one with a 0, one with a 1. And the fact that they share a prefix means this can later be part of a bigger tree, but we're not there yet. And we assign this entire tree now the weight 2, which is the sum of the weights we've previously had. That's the first iteration. Second iteration is again find the two partial tries with minimal weight, these 2, and combine them into a single trie, where again you have a new node. It has 2 edges, 0 and 1, and they both lead to the 2 previous little trees. Okay. And here in this example, one more step where nothing really is chosen, so only 2 things left, so you only have to lump them together. If you were to revisit this first step where we grouped E and O, you now see that U is just 2 zeros. But the way of constructing these tries, or keeping these partially constructed tries and merging them, is a convenient way to achieve this without ever doing the explicit recursion. It's very natural to do this in an iterative way bottom up. Because we're using this notation in the tutorials, I want to stress that this is just the EO character as it was in the previous slide. So that's the new character that corresponds to E and O. But we can also do this at the next level. So we have EO with a box around, and then we combine this with L and put a bigger box around. I'm showing you this because this is a concise way to show the tree without drawing the tree. So this might be convenient to quickly sketch this, say in an exam, right? And then one more go. We have our EO, which is boxed together with L, which again is boxed together with S. And you can go from this representation of the tree to this nested boxes representation by taking away the outermost box, and then there's a left and a right part, which have to be the biggest boxed parts. So if you wanted, you could draw a line, but it's not really necessary. So then the left box is what you reach with 0, the right box what you reach with 1, and then you unpack those boxes recursively. So the result of this process is called the Huffman Tree, which is nothing else but the code trie for the Huffman code. So this contains all the code words for those 4 letters. And if you want, you could write down the table that we've had before. Remember, for encoding, it's more convenient to use this table. So E has 0, 0, 0 as a code word. L has 0, 1. O is 0, 0, 1. And S is just a single 1. And so if you encode lossless using this, you would first put an L, that's the 0, 1. then you would put an O, 0, 0, 1. That's where these come from. And then you have two S's, that's two ones, and so on and so forth. And if you were to decode this, you want to use the trie again, as we've seen before in the other example. So you walk down the trie and find in the leaf what's the character it corresponds to. What's interesting, even on this tiny example, if you compute the compression ratio as the number of bits we needed here, turns out to be 14, divided by what you would need if you represent this tiny alphabet with 2 bits per character, the kind of the traditional or natural way. If you have an alphabet of 4 characters, you use 2 bits per character, then you would need 16 bits. So even here you achieve a compression ratio of 88%, even though this is a really tiny example. So it seems Huffman codes work. This is a remark that is essentially just relevant for assessments. Sometimes if you build the Huffman tree, there are ways where you have to break ties, and either way would be fine. It's just I want you to follow a specific rule so that you all arrive at the same result. For example, even here at this first step, there's the 2 elements. They have the same minimal frequency. So which way do you put them in the tree? Here I put E left and O to the right, but I could have done it the other way around. There's no rule in the Huffman algorithm, as I told you, as I described it on the previous slide, which way to go. Both is kind of fine. There's a type-breaking rule for that, which says when you have 2 characters and you find the smallest, when selecting the characters and there's more than 2 that have minimal frequency, then we select the ones with smallest order in the alphabet. That's the first rule. When we combine 2 trees of different values, then we place the lower on the left. And the third rule is what applies to this example. When we combine trees of equal value, then again we break the tie by what is the minimal symbol in either tree. And so E comes before O in the alphabet. That's why E was left. Okay? So just practice these 3 rules. We'll do this in a tutorial question, so you'll have ample opportunity to practice these. That's just the type-breaking rule I want to follow for the course. It doesn't make any difference. You could use a different one. The compression result would be, the compression ratio would be the same, but you get different codes, and that's just confusing everyone. So we've seen how to compute a Huffman code. What we haven't completely discussed is how to compress with Huffman. And it turns out there's a few different options, but the easiest one is you do a 2-pass procedure over the text. In the first pass, you just keep account of how often each character occurs. After that, you construct the Huffman code as we've just seen it. And remember, you need the weights to go to compute the Huffman code. And so this first phase is about gathering the weights. Then we compute the Huffman tree. Then we have to somehow encode the Huffman code as well as part of the coded text. And I omitted this here because you want to do this in a somewhat smart way to get good compression ratios, but then it gets quite intricate. The practical solution is to further restrict what Huffman trees are used. So essentially, you do another step after this. I don't want to get into this detail. But I want you to remember that you have to store the Huffman code as part of the coded text. It's not really something you can get around. And then the second pass, once you have your code, you do a second pass through the text and encode each character using its code word, as we've seen in the example. To decode this, you read the code that someone encoded in the coded text. Again, we won't talk about how to do this in detail. There are simple ways and there are smarter ways that I don't want to get into. And once you have the code, you can start the decoding as we've seen in the examples. You follow in the try down the path until you reach a leaf. Then you know the first character. You jump back up and continue from there. I note something that will be reoccurring in other compression algorithms. Decoding is simpler or also faster than the encoding step. And usually that's because in the encoding step, we have to analyze, we have to do this recon stage where we have to find the redundancies in the text to exploit them, whereas the decoding doesn't have to do that. It's just told what to do. Okay, before we finish with Huffman, I want to convince you that this is not just a random procedure that seems to work well on an example, but indeed computes the best possible code. As I said on the slide, this is what we want. I want to quickly convince you that this is indeed the case. So we want to prove this theorem. I spelled it out here a bit formally, but let's digest this one bit at a time. We start with a given alphabet and some weights. Then the statement is that the code that we've seen, the algorithm for Huffman's algorithm, computes code words that minimize this expression, same expression as we had it before. I'll abbreviate with L of E because this will appear in the proof many times. We sum over all the characters, the length of the code word times the weight of that character. That's what we want to minimize. And we minimize this among all possible prefix-free codes for this alphabet. So as long as you insist that you want a code that encodes one character at a time, Huffman gives you the best possible way to do that. And the proof is an induction over the size of the alphabet, which is natural because the algorithm also is recursive over the size of the alphabet. It calls itself on a smaller alphabet. So first of all, we should do an induction basis. If I have just 2 letters in my alphabet, Huffman will just assign one the code word 1 and the other code word 0. And that's also the only prefix-free code that we have. So there's nothing really to do. And Huffman does what is claimed. It computes the optimal code among one option. So it works for 2 symbols. Now the induction hypothesis is, suppose it works up to a certain number of symbols. And now we look at the next bigger alphabet size, sigma. And so the sketch only shows the inductive step, where sigma is at least 3. And now suppose we're given an optimal code. This is a proof. It's not a way to compute it. So I get to say, you give me the code and I'll work with it. E star is an optimal prefix-free code for my alphabet with its weights. So because it's a prefix-free code, it can be shown as a try, a code try. And because it's a binary try, there must be 2 leaves, 2 sibling leaves in this try that are at the lowest level. So no matter how you stop the tree, at some point there must be a node that has 2 leaves, and that's at the deepest level. Otherwise, there would always be a dangling edge left. So we can always find these 2 leaves, x and y, at maximal depth. And that's true for any optimal code. And now I'm modifying this code. So remember, a Huffman code starts by picking the 2 characters of minimal frequency and makes those siblings. The optimal code might not do that. It might do something different. So what we'll do next is we find the 2 lowest weight characters, A and B, as in Huffman's algorithm, and we swap them with whatever's in x and y in the optimal code. There could be other characters. Maybe the optimal code found a smart way to put another character down there. But if I swap these down, if you look at the sum up here, we make the encoding for A and B potentially a bit longer. But whatever was in x and y before, we make the code word potentially smaller because we move it up in the tree. And this net change is moving something up, releases weight, and moving something down costs us weight, but the thing we move down has minimal weight. So we definitely can only gain by doing this swap. And since the code was optimal, the new code must be still optimal. It can't be better than optimal. So we find the two characters A and B with minimal weight, and we swap them with X and Y. And that still leaves us with an optimal code. And now comes the trick, which is similar to Huffman's algorithm. We try to find an optimal code for sigma prime, which is our alphabet, where we take out A and B, and we put in this new lumped together character. And also assign the weights. The weight of this is the sum of the weight of A and B. And so if we have an optimal code for this sigma prime, we can get an optimal code for sigma by just replacing this leaf for A and B with the little tree that branches out to A and B. Right. So in a picture, there was some deepest node here where we have these leaves X and Y. And then we replace this by this X and Y lumped together. And we can always go back and forth between these steps. So this was for sigma. This was for sigma prime. The rest above, this is the same tree. So the only change I make in this optimal code for sigma prime is replace the leaf for AB again with this little tree that branches off to A and B. And so we assume we made the alphabet one smaller, so we can use the inductive hypothesis that Huffman computes an optimal code for sigma prime. And so that together gives us an optimal code for sigma that is found by Huffman's algorithm. We exactly mimic how Huffman's algorithm would have done the first step. We pick the two characters from minimal frequency and put them together. And so by the inductive hypothesis, the code that Huffman finds for sigma prime is optimal. And the way it modifies it into a code for sigma leaves it optimal. And that concludes the proof for Huffman. All right, so Huffman always computes the optimal code. We'll also see on Thursday that there's another property of Huffman codes that is a little less tight to this notion of prefix-free codes. That's about entropy, if you've seen that before. But yeah, we'll do that on Thursday in detail. See you till then.